cable splicing course, it would have cable splicing up there. But since most people in here are motor control, I recorded under this one. By the way, these are all our certifications up here that's available to you. ETA is Industrial Electronics. NC3. Have y'all had DC yet? Are y'all taking DC now? Have y'all had DC? Huh? Well, if you've already had DC, we have a certification and it's free. It's a meter certification. It's NC3 meter certification. If you're in DC now, you'll get that certification in DC. But the problem is, once we got approved for the certification, there's a lot of people that was already past DC, and it's a free certification on using meters. So one Friday toward the end of the term, if you can come in on Friday, we're going to do that. We're going to do that for the people who passed DC. And like I said, it's a free certification. You have to do like a 4-hour lecture, and then after that, you can do the certification at home, and it's free. The college, it's not free to us. We belong to the NC3 consortium, and it's part of our fees that we pay every year, allows our students to take these certifications for free. So I'll let y'all know when it's available. But if you're in DC now, you'll get it. Mr. Sanders is teaching DC, and you will get, he will do that at the end of this midterm. SMSCP, this is the Siemens Mechatronics Certified System Certification Program. We offer level 1 and level 2 certification. That's the AUT degree. MSSC currently, don't ask me what MSSC stands for, I should know. We have the ability to do the safety certification. Currently, the MSSC, it is it's a certification test that costs money, but the state of Alabama is paying for that right now. So you can do that certification too. If you're interested in that, we'll see and try to set you up. That's more of online, so you're not really in a class. You can do the online and do the certification on your own. And what else? ETA is about, ETA I think is $140 for the associate certification. The SMSCCP is about the same thing for level 1 and level 2. So you have to pay for those certifications, and unfortunately they're not part of your tuition, even though we're trying to get that approved. So you pay, it's not much, like every semester you pay a little bit of money, and then at the end it's paid for you. We found out it's easier to pay things in installments than it is to pay up front. So we're still working on that, guys. I'm sorry it's not available. So this is a pre-test. Let's see how much of this we know. Some of y'all had quite a few courses, so you don't know a lot of these. So what is the electrical circuit? Nobody in here. Everybody said intro. Y'all should have been. This is a basic thing. We use the term circuit in a lot of our technologies, even in fluid power. Fluid power, we have circuits, right? Understand that. So what is a circuit? What's an electrical circuit? So the definition of a fluid power circuit would be basically the same, except we would use fluids instead of current. So what's a circuit? Huh? Not only a path, it's a complete path. It's a complete path for current flow. Everybody understand that? And so down here, I don't know why it's not up there. What's required by a basic circuit? Gotta have a voltage source, right? Gotta have a push. What else is required? Load. Gotta have a load. You gotta have something out there to do the work. What else is required? Gotta have conductors. Gotta have at least 2 in electricity. Gotta have 2. Right? You understand that? What is an insulator? What's a conductor? Well, electricity or current, so that's technical term, the current, because electricity consists of several different things, right? But here we're talking about current. So it's usually metals. We'll look at this in a minute. What natural metals is the best conductor of electricity? Silver is the best conductor of electricity, followed by copper. Somebody's already had my classes. Copper's number 2. Number 3 is gold. And number 4 is aluminum. Now, why don't we use a lot of silver for conduction? Very expensive. And copper is almost as good as silver, believe it or not. Very, very close to silver. But silver is the best known conductor of electricity. We still use it, but we use it as a plate. We'll look at that in a minute. Everybody wants to say gold because it costs more money. We do use gold as a plate. And we'll look at that in a minute too. What are the 2 most used electrical conductors? I mean, I've had my classes before. What's the 2 most used? So the 4 that we came up with, what's the 2 most used? Copper and aluminum. That's fact. We use copper a lot and aluminum for high voltage stuff. What is voltage? It's very important to understand what voltage is. So what's voltage, yeah? Pressure? The difference in electrical potential. It's push. That's all it is. It's a pressure. Before anything flows, we got to have a force, right? You understand? I've got to have pressure. What's current? Yes, the flow of electrons. What's resistance? What's resistance? Now, what's resistance? Resistance is the opposition to current flow. Got to have resistance. If we don't have resistance, we don't get work. And what's power? Power. It's not energy. Energy, we have to have energy to produce power. Power is work. Well, it's the rate of doing work. It's the rate of this. When you burn power, when you burn calories, you can't sit on the couch eating potatoes. You got to get up off your butt and do something, right? You understand? So it's the rate of doing work. So I can walk a mile in 24 hours, right? Or I can walk a mile in 1 hour. Which one do I do the most work? 1 hour, right? You understand? So it's the rate of doing work. What's the basic difference between DC and AC? First of all, what does DC and AC stand for? Direct current and alternating current. What's the basic difference? Not the applications. We have tons of applications. And we'll look at that too. But alternating current, your polarity, the current flow is changing direction. Always changing direction. DC, it never changes. That's why it's called alternating. Of course, when we get into this, we're going to look at cycle, frequency, and hertz. Anybody know what these are? These are terms we use for AC. Okay, so we're going to learn that. What's the difference between an open and a short? A lot of people, you're going to learn this correctly. Just about everybody that don't know calls it, anytime they've got a problem, they call it a short. I got short out there. My lights aren't working. There's something short. Okay, but you're a technician. You're in the trade, right? You understand? You'll learn the difference. What is an open? Then so it's not a complete circuit. I mean, you have no complete circuit, right? So it can't flow if you don't have a complete path. What's a short? It's undesirable path. So you've lost control of the current. We're definitely trying to control current, right? You understand? It's just like when the waterworks lose control of their water. That's not a very good thing to do, right? Y'all seen these where these pipes bust and create sinkholes and stuff like that. Well, they've lost control of the flow of the water, and that's what's happening with short. Short, we still have current flow, but what? We've lost control of it, right? The basic circuit we are looking at. What's the difference between series and parallel circuit? Anybody know that? And we also have the series parallel we'll look at. These are the two basic circuits that you'll use in motor control. Series, single element, single load series and parallel circuit. We got to pick up the difference between resistance, which is what y'all learned in intro. You learn about resistance. But we have another type of opposition that comes into play in AC called reactance, which is very important, which creates two types of power in an AC circuit. So in a DC circuit, the only power available is true power. In AC circuit, we have both of them. And we'll look at those. It's very important in motor controls, but also in cable classes. So this is just a conduction chart that shows you all the best conductors. There's copper, pure copper, silver copper, annealed copper, which is basically copper that's been heated and cooled to make it softer. Gold is here, and then aluminum. Gold, of course, we have problems with gold. For one thing, it's not the best conductor. So what advantage does gold have over other metals? It doesn't corrode, yeah. So we use gold for a lot of plating. So a lot of times you'll look at circuit boards, and anything that's going to be exposed to the atmosphere, the conductors are still copper, but then the coppers have a real thin gold plating. I mean, a real thing. You know, like some of these companies, they put on these, sell these coins, and they'll say like 0.3 milligrams of gold. So it means if you rub that thing a couple of times, it's going to wipe the gold off, right? You understand? It's extremely thin. Silver, we gold plate, silver plate, what we refer to as contacts. Contacts is when we make a circuit. So your light switch has contacts in it. So contacts, these are basically conductors that we touch together to complete gold circuits, closed circuits. And if we touch them together, we want where we touch them to have extremely low resistance. So we use a lot of silver plating on contacts, and that's about the only place they use silver plating. Silver at is when they coat contacts. And these are other things that drop down. Silver commonly used as platings, copper extremely good, gold commonly used as platings, aluminum commonly used in high voltage conductors, and then copper and aluminum are the most used conductors. So just about all your high voltage lines use aluminum, and then everything else is copper. Physics definitions of some of the things. Force is an interaction that attempts to change the motion of an object. So voltage is a force. Everybody understand that? Everybody okay? Work, the transfer of energy from one physical system to another, especially the transfer of energy to a body by the application. Y'all can read that just as good as I can. Power is what? It's the rate of doing work. In electricity, we do watts, or something called volt ampere. Power is force divided by distance. We don't use that formula because I don't know how far an electron moves, but I do know how fast it moves. We call that current. So current is speed. It's 6.28 times 10 to the 14th or 18th electrons moving past a point in a second. So in electricity, we calculate speed by force. And what's our force? Voltage. And then our speed will be current. So that's the way we calculate electrical power. And I need to correct this. We have two types of electrical power. We have watts. And then we have another unit called volt amperes, which deals with AC. Which we call VA. I need to put a dash in there. So basic stuff. Some of y'all should already know. So all electrical devices operate from what? Electrical current. The amount of power produced by these devices is determined by the amount of current flowing and what? The force that's causing it to flow. Everybody understand that? Now, in intro, I don't think y'all get into power. I think in intro, all y'all got into is current and voltage, right? Did they do any power? Watts? No? Talked about it. But that's what power is. Power is, and you understand, power is work, right? It's the rate of doing work. So when you get your bill, we don't call it Alabama current. We don't call it Alabama voltage. We call it Alabama what? Power. Right, you understand? And every month, you don't get a current bill, you don't get a amp bill, you don't get a resistance bill, you get a what? A power bill. So that's what you're paying for. You're paying for work, but also the rate of doing that work, right? That's power. The amount of current is controlled by the amount of force divided by the amount of opposition to the flow. Now, you did learn that. That's Ohm's law. Of course, in Ohm's law, you learned that I is equal, what's the formula? The amount of current. I is equal to what? Yeah, V or E. Those are both over R. Well, the true formula is I is equal to V over ohms. And what you'll learn in these classes is that we have more than ohm. We have more than resistance as opposition. We have something called reactance. And those are the two types of opposition. So basically, Ohm's law is I is equal to V over the opposition. And of course, in intro, you learn V over R, right? You understand? Because intro in DC, that's what you're going to learn, because in DC, the only thing you have is resistance. In AC, we have something called reactance, which we'll look at a little bit. And of course, this is AC, right? We teach y'all a little bit about AC. There's a lot to AC. AC is probably one of the harder courses that we teach. Anybody had AC yet? James had it. Easy course, ain't it, James? Oh, no. Not at all. It's just like DC, you might get a job where you never ever use Ohm's law. You never write it down, but if you understand Ohm's law, you understand the effects voltage has on a circuit, you understand opposition has on a circuit, and you understand current has on a circuit. And once you get that understanding, then you understand that's going to get you a long way on fixing stuff that breaks. Okay, you understand that? Or even designing stuff. Angles. Yeah, we deal with angles in there, phase shifts. So, electrical current. We have two techniques of teaching current. The predominant way is teaching what actually happens. The other way they refer to is conventional current. So, conventional current teaches particle flow from positive to negative. But what they finally figured, and that's what they thought, because when they assigned polarities, they signed plus, they find negative. And what they did is they considered the positive to be the higher potential. But in electricity, that's not true. It all depends on what we're doing, right? So don't think about negative in the negative side of a battery being minus, like we learn in math. So the negative can be the higher potential just as much as the positive is, right? You understand? So we have negative and positive power supplies that you'll run into in electricity and electronics. So negative power supplies and positive power supplies, but what's actually moving is not the atoms, is what's actually moving in the circuit is electrons. And what's happened is we cause these electrons to move out of their orbit by applying a difference in potential. If we've got enough potential, we can move anything, right? You understand that? I mean, I've seen these big old semi trucks out there, and they bring a dang tractor out there, and they pick them up and move them around. So basically, I've seen them move mountains, right? You understand that? If they've got enough potential, they might do it a little bit at a time, but they can move mountains because they have enough what? They have enough force and have enough pressure. So if we apply a difference of potential, and these electrons see a negative, what negatives have, electrons have the negative charge, then what can happen? It could cause them to move. If it's the right material. And I don't know if this PowerPoint talks about it or not. We'll see. But the way the atoms are laid out, we start off by having what we call a nucleus, which consists of protons and neutrons. And for every proton, we're supposed to have an electron that orbits around it, right? You understand? And then those electrons are spinning around it there. And then they spin in something called shells. And then the shells vary depending on the number of electrons that will be in the maximum number of electrons that will be in the shell is determined by the shell. The outside shell is very, very unique. The outside shell we refer to as the valence shell. The outside shell can have a minimum of 1 and a maximum of 8. I don't care how far it is out. It'll have a minimum of 1 and a maximum of 8. And that's what determines the conduction characteristics of the atom. If it's got 1 out there, it's going to be able to get rid of it easy, right? You understand? If it's got 8 out there, it's going to want to keep them. So this is what defines a conductor. So good conductors are any metal that has one electron in the valence shell. And your best insulators are the ones that have 8 out there, right? You understand? Your rubbers and your Teflons and stuff like that. So basically, I don't know if it's in this slide, but anything that's got 3 to 1, we classify those as conductors. Anything that has 5 through 8, we calculate those as, we classify those as insulators. Anything that has 4, we call those a semiconductor. Have y'all heard of the term semiconductor before? Well, now you know. So anything that's got 4 out there in the valence shell, we call those semiconductors. Because they're neither what? They're neither conductors, good conductors, or they're neither good insulators. So what's actually moving is electrons. Everybody understand that? The strength of the difference in electrical potential and the amount of opposition to the flow of electrons determines the speed of the electron. So we have 2 things that determine the speed. It's how much force you got and how much opposition you're pushing it. It's out there on your car, like you're trying to push a car. You know, you got a little tiny, what do they call it? A little tiny car. Huh? Yeah, you can push those things. You know, you get out there and you get a big old SUV out there, you can't push that thing, even though you're applying the same force, right? Understand? Or if you do push it, you're not going to push it in your same. Everybody understand this? Some materials, such as metals, allows electrons to move freely, while others, like rubber, don't. For this reason, metals make good conductors, and then these other things make good insulators. Now, why do we need insulators? Why do we need water pipes? Why do we need blood vessels? Why do we need blood vessels? Why don't we need blood vessels? Why don't there's blood just out there? Right? Understand? Why do we need water pipes? Well, to insulate, to keep the push in, right? And why do we need blood vessels? To keep the blood in, right? You understand? So that's the piping inside here. So if I'm going to keep this push in, then I need to encapsulate those things in something that impedes the flow of current. And that's insulated. By the way, insulators have current flow in them. It's just that it's so small that we can't measure. Everybody understand that? There's no such thing as infinite opposition. So if I don't have infinite opposition and I put pressure across that, you will have current flow. So there is current flow through the insulator. It's called volumetric current. It's the flow through the insulator. But in plus, I come up here and grab those things. I'm a pretty good conductor of electricity, right? And if I get into a wire that's got a push in it, and then I get across two conductors that has a difference in potential, then I'm going to get current flow through my body. My body has resistance. You push current flow through resistance, you got problems, right? You understand? Because it creates heat, burning up. So we insulate these things to make them safe, plus to keep them. The voltage is the difference of electrical potential that forces electrons to do what? Will do. Current is what? The flow of electrons caused by the difference in potential. Resistance and reactance are the oppositions of flow. Resistance does not vary with frequency and reactance does, so we'll have to learn a little bit about this. We're going to talk about these later to get to it. So we already talked about this. An electrical circuit is a complete path for current flow. The minimum requirement for a circuit is what? A voltage source, a source conductor, a load, and a return conductor. What's so funny about AC? They're constantly swapping. Now this is the minimum requirement. What's the usual requirement for a circuit? One more device. What? Maybe a control device. Yeah, so we got circuits back here, but I have the ability to turn the lights off and turn the lights on. So normally we have some type of control device inside the circuit. Are we okay? So this says minimum. So a good analogy of electric circuit is the circulatory system. This is really good. So here we got, so what does it consist of? We have a heart, right? What's the heart? What does it do for us? Source. Yeah, it creates a difference in potential, right? Which causes what to flow? Blood. Then we have the vessels, which consist of artery and vein. Arteries take the blood out, veins bring it back. But they're all classified as blood vessels. So these are our guys. And so what does the conductor do? What does a conductor do for us? What does a conductor? What's the function of a conductor in a circuit? To get the current from the source to the load. That's the function of the conductor. It's got one function. That's it. And to get it back again, right? You understand that? So we have our arteries. What's the function of the arteries? To get the blood from the heart to the load, and then what's the vein for? To get it from the load back to the heart. That's the functions of the vein, which is what conductors do. And what's the load? What's the load out there? What are we powering? The blood is the power. It's the source of the power. What? We're powering our muscles. So your blood goes to your muscles. Right? And then our brain is another complete thing. It signals the muscles on what to do. But if you don't have any blood flow to if you don't have a power source to your muscles, then your brain's not going to do anything for you, right? Electrical circuit works similar to this, right? The heart pumps blood through the arteries, through the muscles, and then back to the heart, through the veins. So we've already talked about the singularity. Everybody okay? So if you understand that, then you got it now. Voltage is similar to the heart. Current current is similar to the blood flow. Conductors are similar to the vessel, and muscles are similar to the load. So these are basic electrical circuits. So we have to have a voltage source. The battery delivers what type of current? Direct current. Then it goes through conductors, goes through the lamp, and then it comes back to the source. And then of course the work is out there doing, this is out there doing the work. So conductors are not supposed to have a function, but they're not supposed to do work. They don't do electrical work, right? Understand that. They don't create watts. They're not supposed to. Voltage source, source conductor, electrical load, return conductor, and then the load. It's just a light bulb. These are the three types of circuits we'll run into. Motor control, you'll have a single load series circuit. Parallel, you will have all types of parallel circuits. In electronics, you'll have all three of these. Now, series circuits have nothing to do, this is a big problem we have in motor controls, is I'll have about 4 or 5 push buttons out here, I'll have them hooked all different types of ways, and I'll have them hooked in parallel, and people want to call it a parallel circuit. How the control devices are connected has nothing to do whether the circuit is a series circuit or parallel circuit. It's how we connect the loads. Everybody understand that? The series circuits consist of one or more loads connected one after the other. The voltage provided by the source is distributed across the load proportional to the load's opposition. So basically it means the load that has the biggest opposition drops the most voltage. Now, what you got to understand is voltage does not flow. Everybody understand that? What flows is current. But anytime we go through some type of opposition, we lose pressure. We call it a voltage drop. Everybody understand that? So we call it a voltage drop. So the biggest opposition in a series circuit will drop most of the pressure. And the smallest opposition in the series circuit will drop the least amount of pressure, right? You understand that? But every time we go through, and pressure is very important. So anytime you go to the doctor, what's one of the first things they do? Check your pressure, right? Check your pressure. And of course, this causes a lot of problems. We have people that have heart attacks and have all kind of problems because their vessels are not supposed to have almost no opposition, and they get cholesterol built up in them, right? And then they start impeding the flow, and that starts giving them problems, especially to your heart. Since there's only one path, the current through each load is the same throughout the series circuit. So this is an example of a series circuit. Now motor controls, we're not going to do this. Motor controls, we're going to have one load. Or we're going to hook them in parallel. We can have multiple loads, but if we hook them in multiple loads, we're going to hook them in parallel. This would be a multiple load series circuit. And all the voltages are going to be distributed across those loads. And the one that has the highest opposition will drop the most voltage. The voltage source does not move. But what happens anytime you go through an opposition, you lose force, right? Or pressure. Everybody okay? Yes? And the current is the same. So, and these are loads. I could come over here and put 15 control devices, push buttons, and I could hook them in parallel, but that's not what makes it a parallel circuit. What makes it a parallel or a series circuit is how we hook the load. So this is a parallel circuit. This is the way power is distributed at your house. So what happens on this one if I take load 1 out, then we lose a complete path, right? You understand that? So this is like your Christmas lights. Your Christmas lights are actually series parallel. But what happens when one of the lights blows? You lose the whole string because it's a series circuit. And as soon as you lose one, you've lost the path. There's no longer path. And if you don't have current flow, you don't have work. Everybody understand that? Well, that's the problem with the series. But what we can do is instead of having light bulbs out there rated at 120 volts, right, I can have light bulbs rated at 2 volts. But now each one of them drops 2 volts. Then I could have what? I could have 60 of them out there. And that's string. Right? You understand that? Very little old tiny little light bulbs now instead of having one rated at 120 volts. So that's one of the advantages of a series circuit is that each load is going to drop like smaller voltage. If you hadn't had DC, you're going to get into these guys a lot. Parallel circuits. The voltage applied to each load remains the same. All loads are connected across the voltage source. The current is distributed in the circuit inversely proportional to the branch opposition. So this is a parallel circuit. So guys, this is your house, right? Your house is wired in parallel. So what's one of the big advantages of it? So if you could go to any outlet in your house, and you can take your voltmeter and you can plug it into it, and it's going to measure the same. So the voltage is the same all over a parallel circuit. Now what's nice about a parallel circuit is I can remove load, and it don't affect the other load. So I can go back there, I got these 2 lights turned off. Now if this was a series, and of course all these they're not in series. But if they were in series, everything would go out, right? You understand that? So if my house was in series, I go off and I turn off the light and all the power in my house goes out. But what can you do with a parallel circuit that you can't do with a series circuit? You can add and remove loads. Of course, if you add loads, the current load goes up because your source has got to support another current path. If you take loads away, then your current goes down. Everybody understand why? So this is why somebody in your house says, turn off all those lights. Because the less current you have, and power is the rate of doing work. So the less current you have, the less power you consume, right? Understand that? So these you're going to do in motor controls, parallel. So we're going to be able to put loads in parallel. The only other thing we're going to do in motor controls is we cannot have a multi-element series circuit. So what we'll do is we'll have one load over here. But I could come over here and do this, and that's still not a parallel circuit because I don't have 2 loads, right? You understand? I can come over here and do this. By that way, that's a symbol for a push button. And you're going to do a lot of this in motor controls. You're going to do this. Now, this is a parallel circuit. So in motor controls, you're either going to have one load in a circuit, or you're going to have multiple loads. If you have multiple loads, multiple loads are going to have to be in parallel. Everybody understand that? Well, that's only 2 types of circuits. You'll have single load series circuits, and then we'll have multiple load parallel circuits.
I'm saying this right. You can have multiple loads on the same run.
Yes, if they're in parallel.
So you're going to have one on the same line.
Right. You been reading that somewhere?
Nah. Yeah, I took the T class and then in my
PLCs is the same thing. You know, PLCs and motor controls. PLCs program. But we'll look at this later on. This is a diagram we call a ladder diagram, and you can see why it's got that name. And what we do is we take our 2 main conductors and we draw them vertical to each other, and then we put circuits between the 2 lines. So the power will be across the 2 vertical lines, and then we have individual circuits that run between those 2 lines. Between the 2, and we call them, numerically we'll call them L1 and L2. But in true life, they're going to be called something different because you might have several L1s and several L2s, and you need to identify that. And so, the rule is that we only put one load per line. We put multiple loads per rung, but the loads have to be in a motor control circuit. The loads have to be in parallel. So either we got one load. If we have multiple loads, they're going to be in parallel. That's true in motor control and also PLCs. So PLCs, we have different languages we can program PLCs, but the main programming language for PLCs is the language we call ladder logic. And so if you take PLCs first, it'll make this class easier. If you take this class first, it'll make PLCs easier. It don't make any difference which ones you take first. It'll make the other class easier. But there's some things in PLCs. PLCs are computers. So there's a lot of other things that you pick up on there that's a little different, but it's basically the same as far as this rule right here. This is just an example of series parallel. If you're in so in series parallel, some of the circuits are series, some of the circuits are parallel. And in motor control, this is not really important. But if you're in electronics, you'll run into these guys. So this is electronics. So my TV is series parallel. Right, you understand that. My cell phone is series parallel. So these are electronic circuits. Where we have some in series, we have some in parallel. And if you're in solid state, you'll really run into these when you get into transistors and stuff like that. The way we set those things up for operation, we call them biasing. We bias them in series parallel circuits. If you're in industrial electronics. If you're an automated manufacturer, AUT, you won't run into I don't think that course is required. I don't think it's elected in AUT. Control devices. Controls the flow of current and consumes no electrical power. The connections of control devices does not determine if the circuit is series or parallel. Y'all understand that? That's a very important concept. I guarantee you, if I was going to teach the class, I'll throw the first one up here. I'll put 15 switches in parallel, and I'll say, is this a parallel circuit? And somebody in the class will say yes. But what determines if it's series and what determines if it's parallel is how the loads are connected, not the control device. Some of the controls used in motor controls, this is in electricity, switches, push buttons, relays. Everybody's familiar with switches. Everybody's got light switches in their house. And what can you do with that? What do you do with a light switch? But you are controlling the flow. You're either letting the current flow or you're not letting the current flow. So to get work, you've got to have current flow. You've got to have it. Everybody understand that? So in motor controls, we're going to have a lot of push buttons. We're going to put, so this is a basic circuit right here. So this is a true circuit. This is not, I'm sorry. This is the most common circuit. If we got a watt device, we got a control device. We still have a voltage source. This could be AC or DC, by the way, but if it's AC, these little blue lines will be going back and forth. Okay. Then we got some type of device that is the load. By the way, light bulbs don't care if it's AC or DC. And then we got that control device up there that's doing what? Controlling the flow. So we have all types of control devices. Motor controls and in PLCs, the only control devices you're going to run in is stuff that's on and off. That's it. Okay. In electronics, you'll get into transistors. Y'all heard the term transistors? You hear that a lot. They are control devices. That's all they are. They're control devices. They control the flow of current. But switches, these are electromechanical devices. So that something has to open or close that switch. Now, of course, you're used to doing it manually, right? You understand? But you get in your car, there is no way in the world your starter is running through your ignition switch. So you're talking about 50, 60 amps to turn that sucker over. So your switch on your column would have to be big open, right? But what you're doing is you're controlling an electromechanical device called a relay. They call it a starter signal, but it's actually a starter relay. So that's an that's an electrically controlled switch. But what we do is we open and close that switch using electricity. So you can see them up here. These two things down in the lower right-hand side, these are relays. And those are electrically controlled switches. So these are the control devices, guys, y'all run into. These guys, of course, everybody's familiar with light switches, push buttons, selector switches, relays, which are the electro control relays. And sensors, we have what we call sensors. That a sensor is some type of device that takes an electrical stimulus and converts it over to electricity. So that's basically what your sensors are, right? Your sensors. Your brain does not understand smell. Your brain does not understand sight. Your brain does not understand hearing. Your brain only understands electricity and chemicals, by the way. So we got these sensors. We got the sense of touch. So we touch something. We have nerves. It can take the nerves, takes that and converts it over to an electrical equivalent. This comes into our brain, and our brain processes electricity. It's powered by blood, but it processes electricity. So these are called sensors. So we have liquid level sensors, we have pressure sensors, and one of the main things that you'll look at in motor control is some sensors. You have a whole series of lectures on sensors. So these are control devices. But sensors are what we deal with in automated manufacturing. What's automated manufacturing? What does automated manufacturing mean?
Right.
What does automated manufacturing mean? It means making something with little or no human intervention.
What is automated?
Automated manufacturing. So automated manufacturing means making a product with little or no human intervention. Thank goodness it's still no. There's still not a no, right? Understand? We still have little human intervention. But we still have it. But the problem is, what's nice about automated manufacturing is that it increases the skill and the pay of the people that actually do the work, right? Thank goodness. These are motor control loads. We have these devices called solenoids. I know what a solenoid is. I don't know if I got my solenoid, my homemade solenoid. No, I don't. I got my solenoid, but I don't have my nail. Maybe they will work. So guys, go ahead and take a 2-minute break and get these things working. Please. By the way, we take a break every hour. I have a tendency to get all wound up and lose track of time. So about every hour, somebody needs to do what? Do I have any of those in my bag? Oh, there's my bag. Looking for my nail, I got it right. Anybody know what an electromagnet is?
Alternator.
Huh?
Alternator.
Electromagnet. No. Alternator uses electromagnets. So yeah, an alternator uses an electromagnet to generate electricity. Everybody knows what a magnet is, right? What's a magnet? What's a
Know what
magnet?
it is and what it does, I don't know exactly how to find it.
It's well, we have man-made magnets and we have natural magnets, right, that exist in nature. But these are minerals or devices that attract ferrous metal. Okay. So an electromagnet we can create magnets too using electricity. Anytime we push current through a conductor, it creates a magnetic field around the conductor. And if we wind the conductor in the same direction and then we concentrate it to a piece of metal, then we can create what we call an electromagnet. By the way, the coupling between the conductors, so every one of them, we get a little tiny magnetic field. And then if we wind it in the same direction, the magnetic field in each wire combines. But you got to have what we call a coefficient of coupling, which means the insulation on the wire is going to be extremely thin. We call this magnetic wire. And since it's extremely thin, we got to be real careful with it, because if you rub off the insulation, then you can create shorts, right? You understand? We can do this with AC, and you'll learn about that, how we do it with AC, but normally this is DC. DC is a lot easier to do electromagnets with. So this is an electromagnet, and what I'm going to do is just going to connect it up. Now, what advantage does an electromagnet have over a permanent magnet?
Electromagnet, you can turn it off and on.
Turn it off and on.
Make it take apart for the permanent magnet.
Or we can control the strength of the field. So how much current you put through the conductor controls the strength of the field. One way we produce electricity, and this is the way your alternator works, guys, is that when I swing a conductor through a magnet, it induces an electromotive force, or it induces a voltage into the conductor. So what we have over here is we have a magnet, and then we have and what happens is that, this is not going to be recorded, so this is just a bunch of loops of wire. So when I swing a wire through a magnetic field, it induces a voltage, it absorbs the energy of the electromagnetic field and turns it into a voltage. And if one little wire gets a little voltage, but if I do a bunch of loops of wire, then each voltage adds together, right? So we gotta have a bunch of loops of wire. So all I'm gonna do, this is a little ammeter down the
minus and positive voltage. And all I'm gonna do is just run the wire to that thing. So I'm producing a electromotive pulse. Now if I spin it, it goes that way. Now it goes the other way. If I spin it, it makes that sense. You don't understand that? So all I gotta do to produce a voltage is spin a magnetic field. I can either spin the magnet or I can spin the field, right, the outside, and I can induce the voltage. If I spin it though, naturally it's going to create AC. So we call that generator out there on our car, we call it an alternator. How's it creating voltage? It's spinning a magnetic field, and the magnetic field is cutting a bunch of conductors. But the spinning field is an electromagnet. So what determines how much I get? Well, there's three things. There's how many loops of wire I put in here. Every one of them would add a little voltage. The other thing would be the strength of this field. Right, you understand? And the other thing would be the speed of the motion. So this guy can't keep up with it. But the faster I go, the more voltage I get. So literally what's happening out there is that when you're accelerating your car, your alternator's all over the place. So if we didn't do something, when you were going, it would burn up your lights. When you was idling, you wouldn't have any lights. Your air conditioning up. But what we're doing is we're controlling the strength of the field. So the stronger the field is, the more voltage we put out. So we've got a thing called a regulator on your alternator, right? If it senses the output of your alternator going down, it increases that spin in the electromagnet. And if it sees it's trying to go up, it decreases the strength of the magnet. So you have what we call a regulator. So if you go out there when your car's running and you take your voltmeter and put it across your battery, it's going to measure about more than volts. So that's what lead acid batteries are voltage store. You have to put more voltage on to cause them to fall. So you can tell if your alternator's working in a heartbeat. You don't have to go to the autobahn and come out there. You take your voltmeter out there, you crank the car, you can get it cranked, you can jump it off and crank it, and it's putting out 14 volts. Your alternator's fine, right? It's probably your what? Battery. When you turn it off, your battery should set up around 13 volts. If you set it overnight, and you shouldn't see it drop. Overnight, it'll drop down to what it calls. It'll drop down to 12 volts. So if you turn your car off and you put your meter on that battery, and that voltage starts dropping instantly, what do you know that? Battery. So you can check the battery out and know that. So that's making AC. That's making AC, right? But if I put current through a conductor, it creates a magnetic field. And that's what we're doing. So you're using electromagnet. All generators use electromagnet. Right? Any generator that you have the ability to regulate. Regulate means we maintain a constant output. Because if we didn't do that, you turn on your air conditioner, the voltage would drop. You rev your engine, the voltage would go up. If you got that regulator out there that's doing what? Sensing the output of your alternator, if it tries to go down, it increases the field. If it tries to go up, it decreases.
Question.
You don't know what I'm talking about, I can tell you.
Like a main purpose involved in the car.
Run the car. Your battery's there to start your car. It's the only time your battery should ever be used to start your car. And then your alternator is running. Now, your car runs off DC. So we call them rectifiers. These are circuits that convert AC into DC. And then the regulator is called in your alternator to maintain the constant output. So it's electricity, right? So electricity don't really exist in nature. We have electric eels, we have natural things, lightning bugs, they create electricity. Batteries create electricity. Or we can create electricity electromechanical, right? Which is what alternators do.
It was kind of like, I guess, on my head, something going wrong with your car, it won't start. Some people like your battery, somebody like the alternator.
Well, it depends. It depends. if your alternator is bad, it won't charge your battery, and your car is running off your battery. And what happens to every battery if you use it? What do? They run down. So if your car is running off your battery, the battery will run down.
Usually tell when it's running off the back. Or alone.
Could. Depends on what you're running. If all you're doing is, and we have, I mean, it depends on what you're running. So if all you're doing is driving your car, your spark plugs don't use much energy at all. It's all that other stuff that uses energy. So you can run off a battery for a long time if you don't use anything else. If you don't use your headlights, if you don't use your radio, if you don't use your air conditioner or power home.
I go measure the battery, get 14 volts, and take it on my alternator.
That's it. That's all there is to it. 14 volts, about 14 volts, a little over. And then when you turn it off, your battery should, we call it a surface charge. So you've been charging it with 14 volts. So when you turn it off, your battery's going to measure about a little over 13 volts. And if it starts dropping instantly, then you got a bad battery. Oh, here's my electromagnet. I'm going to hook up some wires to it. So this is, we have to have a real good coefficient of coupling. So this, like I said, this is what we call magnetic wire. So you wouldn't wire anything with it because if it got hot, it's going to burn the insulation off of it. And then, where's my other lead at? I guess it's a word. I'm trying to keep my fingers out of it. And I didn't have any jumper wire, so. And so, so this is an electromagnet. And then what's nice is I can turn it off. That's an electromagnet. You see these all the time. You wonder how these big scrap bins, they got these big cranes, they drop them over and pick, that's an electromagnet. That's all it is, just an electromagnet. And once they pick, if it was a real magnet, once they picked it up, they couldn't drop it. But they can swing it where they want to and turn the power off and it just doesn't, it drops it. But another advantage is we can control the string. Now we've taken this a step further and created this thing right here. Let me turn off my power supply. So you got to understand, you got to use a lot of wire. Some people think wires have no resistance, but that's totally false. Wires have resistance. So what we have to do here is we have to use a lot of wire because that's the only resistance we got is the resistance of the wire. So this is a device. Now notice what I've got here. This is homemade. I've got a straw and I wrap my wire around the straw. And then I'm going to come up here and hook this up. And I stripped off the insulation. That insulation is so thin, and I've seen a lot of people strip the insulation with a cigarette lighter. Just put a cigarette lighter on it and just disintegrate. But what I'm going to do is I'm going to take this nail and I'm going to come up here and put it on there. And then I'm going to turn my power on.
Just like the other one you had,
a little motor. No, that was a motor. This is a device we call a solenoid. SELONOID. NOID. So what a solenoid does is it takes this magnetic field and it creates a linear motion. So when I turn the magnet on, when I turn this on, it sucks that nail up into it. And then when I turn it off, it does what? Cross back. So what can I use that for? Yeah, everybody say, buzz me in. Buzz me in at the front door. Well, that's what it is. The lock is a solenoid. And somebody's got a button somewhere, they press it, it pulls that rod up and you can come in, right? You understand? When I was in the hospital at UAB, they lock up all types of doors trying to get through. I looked at most of it from the ceiling. But those interns or those guys that was moving me around, they just have a badge that's white, and the doors would open. Well, what was keeping them locked? A solenoid, right? You understand? We can take that motion, by the way, and we can use it to close switches. So we can use this. I can go over there, I can move that switch, but why can't I hook a solenoid up to it, right? You understand? And use the solenoid to do what? Close and open the switch. By the way, solenoids only create force in one direction, so we have to do something else. So what's causing this to drop down is gravity, right?
One direction.
Yeah, it creates force in one direction, and then something else has to make it turn back. So we use springs. Huh? What's that?
In the electromagnet.
The electromagnet is used to pick up things. So some of our relays use electromagnets, some of them use solenoids. A solenoid literally jerks a metal rod up into it, right? And drops down. So a solenoid would always have that metal rod. And what we do is that metal rod is going to be pulled up into it by putting electricity on it. And then what? But you got to understand, if the nail was long enough, it's going to center out. If the nail was long enough, it would pull in on one side and it would stick out on the other. Right? Y'all understand that? But a solenoid uses that. A solenoid takes electrical energy and converts it into linear motion. But we can take that motion and do a lot of stuff with it. And like I said, we could take it and turn a switch on and then let something else turn it off, right? Like a spring. We'll show y'all the solenoids that we use on most relays have a spring on it. And we'll get one where you can actually see it. Most of your industrial relays are encapsulated in plastic because that wire is so fragile. In the industry, you're banging stuff around, and if you put that little wire, you knock that insulation off of it, you got a problem. Your relays that's in your HVAC system, these you can actually use to see the coil from. So this is a relay. This is a relay we call a control relay. And what I want you to look at is you can see where it actually makes and breaks the circuit. I get my chair tangled up and stuff like that. By the way, I run over on my motorcycle back in 2008. We'll pass this around and let you look at it. But this is a relay. Here's the solenoid right here. So this is the solenoid. It's encapsulated in plastic. So if you bang it, you won't mess up those little magnetic wires, right? And of course, this is where we bring our power into the solenoid. And then when I energize the solenoid, if I can get my camera out, when I energize the solenoid, I'll get this in a minute. I'm going to pass this around to you guys. And then it's got a what on it? It's got a what? Spring. So what happens when I energize it, it pulls into it, right? You understand? And of course, the other side would extend out. And these are where your switches are. And of course, in motor controls, we don't call them switches, we call them contacts. So this set of contacts, when the solenoid pulls it in, this set of contacts closes, so it completes a circuit between here. This set of contacts, excuse me, open. This set of contacts closed. So we'll talk about something called normally, Mr. Sanders will talk about something called normally open and normally closed contacts. And y'all learn what that's like. In PLCs, you program them on here, you actually see them. So we call this guy right here a relay. By the way, when it gets around, y'all bring it back up here so they don't get scattered down. Here we go. And we have different categories of relays that y'all learn in motor controls.
We have what we call control relays, and we have contactors, and we have motor starters.
Well, what I can do now is I can do what with it? I can electrically control a switch. So instead of me going over there flipping on the lights, right, you understand, then I can electrically switch them on. So my car, when I get out of my car, I leave my headlights, most people's are now, you know, they work automatically. And then I just get out, and what do? After a while, they turn themselves off. What's doing that? A relay. So out on your, they call it out on your, under your hood, there's a big black box out there. It's usually black box. And, that's going to be your relay box. If you open it up, there's 15, 20 relays in there. And what it does is that we can get a current gain out of them because your contacts can carry a lot more current than your coil, right? You understand what I'm saying? And also we can use different voltages, which is pretty neat. I'm looking for my, I think I'm going to get this out first. So these are relays. This is the solenoid, by the way. So if you got a washing machine, what turns the water off and on while it's working? Solenoid. It's got a rod that jams up in there, turns your water off, right? You understand? And then when it wants to turn the hot on, it just opens it up. Solenoid. You got an ice maker in your house. What turns the water off and on in your ice maker? Solenoid. Right? It just uses that rod to come up there and plug up the hole, right? You understand? Washing machines. Usually we have a starter solenoid that pushes your whole starter into the flywheel in the back of your car. That's a big old solenoid. So your starter don't stay engaged all the time. It's just when you start it, there's a solenoid out there, and the actual rod, the gear, it's actually pushed out by that solenoid. And then you have a starter relay because your ignition switch can't handle the current required by your starter. But your ignition switch or your electric engine control module could pull in a relay, and then the relay can handle the current, right? You understand? Usually your starter relay and starter solenoid are all part of the same unit. Symbols of the trade. We have things called schematics, wiring diagrams, line diagrams. These are used to represent circuits. And so instead of us drawing pictures, normally we use symbols to represent things. So to be able to read the prints that are part of your trade, then you need to learn a bunch of symbols. And as your tenure here at the college, you're constantly going to be adding to your repertoire of what? Symbols. So what we're going to do, like a road map, and this is pretty good, they have symbols that represent different things, right? You understand that? So instead of drawing a road, they draw a map, which is, these are some of the symbols we're going to use in electronics. Anybody know what this one is? It's a DC voltage source. So batteries are DC voltage sources. Originally, this is basically what we had, but now any DC voltage source would be represented by that system. Whether it's electronically produced DC or whether it's chemically produced DC. Anybody know what this one is? This is an AC voltage source. So the one on the left is a DC voltage source, the next one is an AC voltage source. Anybody know what this is? Yeah, this is a true resistor. Anybody know what this is? I have the biggest problem teaching this. This is a connection dot. And in this class, we have to do that. So normally, if we don't have that dot, there is no connection. If we do have the dot, there is a connection. So if you were taking my motor controls class and you just drew wires coming into wires, and you didn't put the dot there, and I would count off for it, right? I don't know what Mr. Sanders does. Hopefully he don't do Unfortunately, in PLCs, they don't put the dots. I wish they did, but they don't. So PLC diagrams. This is represents a coil. We call it an inductor. Now we'll talk a little bit about these. These guys if you put them in DC, they act like wire. If you put them in AC, they perform differently. This is pretty good. We got them up there. Every one of these lights right here has one of these devices in there. They call them ballasts. Have you ever heard of ballasts? Basically, all they are just inductors. This is a capacitor. In a DC circuit, it acts like an open. In an AC circuit, it don't act like an open. It does a function. We'll learn about that when you get into single-phase motors. They do a unique thing that causes a single-phase motor to spin. So if it wasn't for inductors and capacitors, there would be no such thing as a single-phase motor. No such thing. Anybody know what this is a symbol for? That's symbol for a transformer. That varies depending on what type of transformer it has. We have center tap transformer, multi-winding transformers. Normally they'll put a dashed line in here indicating the core. Anybody know what that is? Huh? Now that's a single pole, double throw switch. Poles are the number of switches. Throws are the number of positions that will control a circuit. Double throws. So throws are the number of positions you can put it in. So a wall switch is a single pole, single throw. But they don't, sometimes they do. If you look at some of the switches down at Lowe's, they'll have SPST on them. That stands for single pole, single throw. Of course, most electricians call these snap switches or wall switches, which is probably what you have. But that's a single pole, single throw. So the number of poles is the number of switches. And then the number of throws is the number of positions you can put that switch in that controls the circuit. A what? A dimming switch is not a switch. It is usually an electronic circuit that uses something called a triac. And it does have an on, but once it's on, then you actually control the power going through your light bulb using an electronic device called a triac. Well, a double pole, let's say a double pole, single throw. So what I would do is I would come over here and I'd have one switch. Then I would come over here and I'd have another switch. Oops, sorry. And then I would come over here and I would put a little dashed line, which means they're mechanically interconnected. So you'll have one operator, but inside the switch you have two. This would be a double pole, single throw. We have two switches. Yeah, they both close at the same time. This would be the symbol for what we call a double pole, single throw. There's two switches, but each switch can only control one circuit. The number of switches. Relays, it's the number of contacts. So it's number of contacts. So what you were looking at there was a double pole, single throw. One of them was normally open, one of them was normally closed. So if you look at that relay we passed around, you see two contacts up there. So that would be two poles, right? You understand? And each one of them only control one circuit. So that would be what we call a double. How would that one be a single pole? Which one? It has two throws on it. Notice, anytime we put a dot, so normally when we have a connection or that we control, this indicates you have a connection. These dots usually mean you connect to. So if it's an open, we call that a terminal or something you can connect to. So notice this one don't have a dot on the top. It's only got one dot. The one on the bottom has two dots. Yeah, so we didn't just finish it. Normally what they would do is they would just extend very small little wires out here. So that would be one switch that controls 2 circuits, and that would be a single pole double throw. And then if I put 2 of these together, and then put the little dashed line, what would that be? That would be a double pole double throw. And your relays are going to be called this, right? You understand? So I think our control relay, I think, has 4 contacts in that, so that would be 4 poles. And each one of them is a double throw, so it'd be 4 pole double throw. Usually, the maximum we'll do on this one is 2 throws. And then after that, we call it a selector switch. So a selector switch is a term we use for a switch that has usually has more than 2. By the way, this is a symbol of a ground, which is probably the most misused symbol in electricity. And we have another symbol that I needed to put up here, and it's open. This is the symbol for a common. What's the difference between a ground and a common? Technically, really, a true ground and a common. A ground is a rod that's drove into earth. It's got to be a copper rod. It used to be copper, now it's usually copper plate, because it's just what contacts with the earth. So I really don't. So the center of a copper rod has really nothing to do with ground, because it's not in contact with the ground. So just about all your ground rods now are some type of metal, and then they're plated with copper. So my phone, do I have a rod driven in the ground and got a wire connected to it? Now if I do. Yeah, but if you went out beside your house, right, you understand, you went over there by your meter box, there's going to be a copper wire coming out of your box. It's going to run down, and there is a ground, there is a rod driven in the ground. Your house is connected to that. And if you go out there where the transformer's at, there's going to be a copper wire running down the side of that pole, right, you understand, and there's going to be a rod, and that is a true ground. A common is just a common connection point for circuits. That's all it is. So this guy right here runs a common. Your car does not have a ground. Your car has a common. But if everybody uses the term ground for everybody. But we do have 2 different symbols. We have the one with the 3 lines. This is the true symbol for earth ground. And then the triangle is the symbol for common. And that's the true symbol.
That's like how you were saying on your car when somebody said you got to grind your car.
Sure, yeah. Yeah, your car has a common. This has a common. There's one conductor in here that's the return of the common for the thing. The meter we call that black lead common, but that's not circuit common. That's meter common. So the black lead is meter common. So your meter's making a measurement relative to that black lead, right? And AC don't care. AC literally has no polarity. So I see people do that. They want to put that black lead on the common for an AC circuit. You look at this, it has no sign. So you measure AC with a meter, red lead, black lead, don't make any difference, right? And when you're on DC, it makes a difference because of the polarity. A digital meter don't care if it's minus or positive. It was really, when we had these pointer meters that we had to use, they only deflected one way. So you always had to put the black lead toward the negative when you was measuring DC. If you didn't, you'd peg your meter out and you could actually bend your meter. Point. So there's a little thing something. So then in digital meters, they don't care. If you put, even on DC, if you put your red lead on your minus and your positive, and your red and your black lead on your positive, your meter's going to measure negative. But 12 volts is 12 volts, right? And it's up to you to understand what polarity that you're looking
So this is ground, this is common. Alabama Power, by the way, we call it neutral. Neutral is a grounded conductor. Anybody know what this is a symbol for?
Fuse, yeah. And there's another one too, that, it's this guy right here. Anybody know what that is symbol for? Circuit breaker. And they draw it open like that. That's the symbol for circuit breaker.
At the bottom of what it's called now, what's the last one?
This one?
Oh, yeah.
This is a fuse. I thought everybody heard that. So what's the difference between a fuse and a circuit breaker? What advantage does a fuse have over a circuit breaker? I guarantee if you went out to US Steel, you're going to see more fuses than you are circuit breakers. They do have some but they're very expensive. They're magnetic circuit breakers. Those guys are fast, but they are very expensive. Usually the ones in your house runs off of kind of, so they take a little, so they're not real fast, because they gotta do what? They gotta heat up. And then, I was giving you my explanation. We do have some high-speed circuit breakers, but they operate off magnetics. So what they do is they create an electromagnet coming through there, right? If the magnet, if it gets too strong, it pops, which indicates you got those things are fast. Yeah, we got some circuit breakers that trip in half a cycle. They're really fast. But standard circuit breakers, like the one in your house, they don't operate like that. They're not really expensive. They're expensive compared to fuses. So the big advantage of a fuse is they're what? Yeah, for the same current. So fuses are less expensive, right? You understand? Circuit breakers are resettable, which means you can do wrong. Yeah, you can reset them. Fuses you can't, unless you put a piece of aluminum foil. Or a welding rod. There were some places out of US Steel over in Inslee, this is true, where they had a welding rod across the fuse. Well, that thing keeps blowing. DC voltage source, AC voltage source, a resistor, a connection point, an inductor, a capacitor, a transformer, a single pole, double throw switch, a ground, and a fuse. These are some symbols that you'll be using in motor controls. And these are in the back of the book. Should be on Blackboard too. And understanding symbols is really, 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 really important because your diagrams are going to be drawn using symbols. We have something called a pictorial drawing, which y'all probably seen. So I go out and buy a new DVD player. That uses a pictorial drawing where they actually draw a picture of this, right? You understand? And they show the wires and have a picture of your TV, which is okay for consumers, but they take up a lot of space. But they're easy for people that don't have any electrical experience to hook things up, right? You understand that? Or even to troubleshoot. But when you get into the field, engineering and stuff like that, they're going to use tons of symbols because they occupy a lot of space. Right? You understand that? So I don't know what page that is in the book. It's probably different in my book, right? I thought the book was over here. Mr. Sanders usually it's the current version over here. So I didn't bring mine over. This was one that's been over here for ages.
Same book, right?
Same book. And if you get the older book, you're okay. It's just that when he says, turn to chapter 5, they rearrange. A lot of times when authors come out with new books, what they do is they split chapters up. And that's what they did in this one. So used to in the older book, they covered all this in one chapter. And what do they do when they come out with a new book? Split it up and add in more chapters. So you'll just have to figure out where the information's at. The information is in the book. Whether you get an old book, if you get a used book. So buying a used book in this class is fine. Even though it really bothers me is you're in this trade and you sell your books. I can understand selling English books. I can understand selling math books, all these other books that you'll probably never use. But these books right here, this is a really good book. It's a really good reference book. Yeah, really good reference. Covers power distribution, covers some solid state, covers some PLCs, which we will get into that. Covers motors, the different types of motors, how to control them, how to reverse them, how to determine what they are, if the market, if the panel. If the biggest thing when people rebuild a motor, a lot of times, and over time, that little thing over there that shows you how to wire it, we call it a nameplate, this big. And you got a 12 lead motor, you got 12 leads sticking out of the side of that thing, and you know, a couple $1,000 and you don't know how to wire it.
You going to have access to this next slide?
What's that? This is going to be access. This is motor control. So this should be, when you go into motor controls, it should have lecture 1, and this is there.
Now, is
Like I said, I don't have access. Mr. Sanders is using my Blackboard site. All he does is copy it open. So all I can do is show, but I can't tell you 100% sure, but it would really surprise me. He uses the same PowerPoint, so these lecture slides will be up there. No, but you have to have a lab book. But you're not in motor controls anyway. You're in cable. Huh? Yeah, you can't use a bar lab book. You can't use a used lab book in motor controls. Don't tell me.
I thought for that.
Because it's.
Huh?
Yeah, because if you buy a used lab book, those people turn in their labs, right? You understand? And then, so you'll get a lab book, and this has happened to me more than once, even though I bring it out in class, somebody will buy a used lab book, and then they want me to provide them the labs that's not in there when they shouldn't have bought it anyway. Well, I don't have any of these labs. And don't rent it either, because y'all got to turn these labs in. So I know they let y'all rent books down there, but you can't rent a lab book, right? You understand that? And this is a really good book. So this is a ladder diagram. Motor controls and PLCs, these are the guides you're going to use. Can you see why they're called a ladder diagram? Because they're basically, so your two power lines, which we generically call L1 and L2, these are your two power lines. This is considered, L2 is considered to be the common, okay, of the circuit. And then you connect circuits, and this is considered to be what electricians call a hot side. And then we connect circuits between L1 and L2. Each circuit we call a rung. And you'll see why. Pretty obvious, right? You understand? So all our circuits connect between L1 and L2, or whatever you call it. You'll look at some diagrams that actually came from USD. Just to show y'all what we're teaching you in here is what the industry uses. And we get into line numbers and how we lay things out. So all your control devices is between L1 and the load, and then the other side of the load hooks up to L2. The only thing that's allowed in L2 is these things called overloads. You get to learn what those are. These are for motors. So this relay is called a motor start. One thing about an electric motor cannot be stalled. If you stall an electric motor, that's what will happen to it. They'll burn it up. Guaranteed. Or a motor, when you put power on it, it better start. If it don't start, you'll do what? You'll burn it up. So we have sensors on a motor, on a relay that's designed to control motors. We have a sensor on there that senses either when the motor don't start or if it stalls. And it'll de-energize the relay. And these are called motor filters.
That's basically the way, like, so your control devices are where? Between L1 and the load, and then the loads connect to L2. Unless it's a motor starter. If it's a motor starter, then you have these things called overloads that motor controls will run about those ways. So these guys up here, these are motor starters. So if you look at that unit down below them, this is the overload circuit. By the way, these are industrial grade relays. Everything you read in this lab is industrial grade. So you're actually seeing what you're running through when you're out there. Except you have to wire them up. So what we have at the end of each module is we have a set of female banana plug jacks. And then you have all the cabling that you have over there. They are terminated with a male banana plug jack. So this is the way y'all connect to the circuit. So you have these terminal boards at the top. These are just what we call manufacturer numbers. These are assigned by the manufacturer. And all they did was transpose them from up here on the actual contactor itself. And these right here are the overload sensors right here. Whoop. These are the actual sensors that sense if the motor tries to draw too much current. So the diagram doesn't show you the sensors, it shows you what trips or drops the relay out, right? Does that make sense? Here, so this is a relay. This is a type of relay we call a motor starter. So you should have two of these. You do your inventory. Stop my PowerPoint right there. So you need to learn these symbols, and it just tells you where to learn in your motor control book. And you're in cable spots and blah, blah, blah. This is a light bulb or luminary. This is the contact we call a normally closed contact. You learn about those. This circle right here is a relay coil. That's the actual solenoid itself that actually causes the armature. And this is the push button, momentary contact push button. Normally open contact, and this is normally closed. You'll learn about this as you go along. I know I'm kind of throwing this out at you, but this is what you're going to learn in motor control. How to read these and how to wire the circuits up. And what each one of those symbols will work through at the time. This is the ladder diagram. You can see the multiple rungs. So this is a parallel. This is a rung. This is still a circuit, but this is a parallel circuit. So notice all the loads are hooked in parallel. So in motor controls, we don't have multiple load series circuits. We do have what we would consider a series circuit, but it's a single load circuit, right? One load per line. Multiple rows, you can have multiple loads per row. So, the one at the very top would be a single element series circuit. The one down below that would be a parallel circuit. Now notice your control devices are hooked in parallel and series parallel, but your control devices does not make it a series circuit. It does not make it a parallel circuit. It's the way we connect the loads, right? You understand? So we don't have any multiple load series circuits in PLCs or in motor control. The problem, what's nice about PLCs, if you try to do it, you're going to get an error. Because it's a computer, it checks up on things for you, right? If you did it on motor control, then neither relay would work. Because the voltage would be divided out among the loads, right? You understand that? So instead of one relay getting 120 volts, it might be getting 60 volts because it's sharing it. Because as soon as the current flows to the other device, it drops a voltage, and neither one of them would come in. So if you hook them up in series, they're not going to hurt anything. Nothing will work. This is a commercial wiring diagram. So if you're in commercial or residential wiring, what do you got to learn? You got to learn symbols. If you didn't understand these symbols, you couldn't wire it according to the way the engineer or the architect designed it. Right? And if you don't wire it according to the way it was laid out, you could cause problems. You might put a wire someplace where it's not supposed to go, right? You understand? And the dang thing works okay, and then it burns down, and they come in there and start checking up on you and find out the whole dang thing was wired wrong. And then I, as a contractor, I wouldn't be in business very long because I'd be getting sued all the time, right? By the way, you can wire, y'all can wire your own house. You don't have to get it inspected if you do. This is an electronic schematic. And you can see this is series parallel. So a good class to take, by the way, if you're in industrial electronics, a good class to take is residential wiring. It'll save you a ton of money. Because once you learn how to do it right, you can do a lot of wiring yourself. I've never had an electrician out of mine. My house is still had burned down. So this is an electronic schematic, but it still all deals with symbols. If you don't, and you got to understand, the circuit does not appear like the symbol, right? You understand? And it's not even laid out the same. So when we lay these things out, we lay them out logically. Normally, inputs on the left, outputs on the right. No matter how they're laid out on the circuit, this is the way we wire them. And you might come up here and your relay might be over on the left and your push button might be on the right. But electrically, they're wired from left to right. Are we okay? Learning symbols. So here we go, motor controls. This is, I don't know, let's see, it's back in the appendix. So this guy here's got a really good appendix. So I've got a marker right here. This is back in, on this book it's 680, it says 658. What it's in your book, I don't know, but it's in the back of the appendix. It says symbols. Not only does it have symbols for motor controls, it's got electronic symbols in here. It's got, we don't have residential. We do teach a class called blueprint reading, even though we don't have blueprints anymore. But they're still called blueprints. The way they used to make these big blueprints is they'd have a chemically coated paper, and they used, like, it was white lines on a blue background, or it was blue lines on a white background. And so these got the name as blueprint. So a lot of people now call any print, they call them a what? A blueprint. And you hear that all the time. Is it wrong? Probably not. I mean, probably yes, but it's just a simple. It's just like using the term ground for a comma. Is that wrong? No. Right? You understand? But you need to understand the difference between a true ground and a what? And a comma. Everybody okay?
So it's schematic.
Huh?
That is you said everybody calls, you have to print blueprints now.
Well, they don't. Some people do.
Yeah.
You won't hear me do it. I call a schematic. So here we're going to deal with ladder. We're going to deal with ladder diagrams, and we're going to deal with wiring diagrams. So that's two different diagrams you're going to deal with in motor controls. Okay. And that's what they are. But you're going to run into somebody that's going to call a ladder diagram a what? A blueprint. Is it wrong? Nah. But you won't hear me call them a blueprint. Right? Because they just don't know any better. It's like my mother, anytime she had a problem, she had a short. And I'll go over and say, Mom, it's not a short, it's an open. When you gonna learn this? Did I do that? No. I went over there and fixed it. So just about everybody, when they've got a problem with an electrical circuit, they say they got a short. Or shortage. I like shortage.
Short someone.
So if you use that term, shortage, I'm gonna say, yeah, the only shortage is right there, right? So, because you're in the trade, right? You understand that. And a lot of things about getting jobs and keeping jobs, when you interview, you're talking with people that know the trade, right? You understand. So when we hire an electronic or electrical instructor over here, I'm on the committee. Why am I on the committee, a hiring committee? Because Miss Herndon, she's the counselor. She has no idea what an open and short is. But if you came in there and you didn't know, if you misuse phrases, right, common phrases in the trade, then what am I going to do? You're not going to get my vote, right? You understand? Because I'm not going to want you teaching my students or our students here the wrong terminology of the trade. So you as engineers, the analogy I use, if I walked into a doctor's office and he turned around to his nurse and says, give him about that much of that. Give him about that much. What would you do? Or Mr. Raymond, I think you're having problems with your thingamajig right here. What would you do? You'd be gone and say, well, I need to go to the men's room, right? Yeah. So if you can't speak the terminology, the problem with doctors is they use a lot of terms. They have to dumb it down a lot for us. So you need to learn you need to learn push buttons. You need to learn contacts. You need to learn coils, pilot light, transformers. So you're going to get a little transformers in motor control. Because one thing, what does a transformer do for? Steps up or steps in what? Voltage. Transformers do not.
Real quick.
Huh?
Real quick.
Yeah, the problem is they also change current. Most people say, huh? What a transformer don't do is a transformer doesn't change power. So technically, if my transformers were 100% efficient, when I turn on a 100-watt light bulb at my house, Alabama Power would give me 100 watts. We don't change power, right? You understand? Y'all understand that? So what happens is that the big formula that we have is we have power. What's the formula for power? Anybody said that? No, V times I. That's the rate of doing work, right? You understand that? Well, I is equal to P over V if I transpose that formula around. So what does that mean? What's Alabama Power trying to give you? What they're trying to sell you? What are they selling you? What are they selling? What's the name of their company? Power. They're selling you power. But they've got to get that power. So the power here at Lawson State, in Bessemer campus, not the Birmingham campus, comes from the Tennessee Valley. How in the world can they get that power all the way from the Tennessee Valley running it through wires? Every wire has resistance. If you push current through resistance, you drop a voltage. They refer to it as line loss. So how in the world can they get this gigawatts of power to the city of Bessemer all the way from the Tennessee Valley? I is equal to P over V. So I'm trying to send you 1,000 watts of power. If I do that at 1 volt, that's 1,000 amps. If I do it at 2 volts, that's 500 amps. If I do it at 1,000 volts, that's 1 amp. Right, you understand? If I use 750,000 volts of 1,000 volts to push that current, I could send you 750,000 watts of power with 1 amp of current. But I can't bring 750,000 volts into my house. So what do we have to start doing the closer it gets to us? We have to start stepping that voltage down. But when you step the voltage down, to deliver that power, the current goes up. So that means I got to use bigger conductors. right? You understand that? So what do we use high voltage? What do we use high voltage for? So you got two voltages at your house. What's the two voltages at our house that we call them? They can be quite a few. What's that? 120 and 240. What runs off 240? Your high wattage devices. Probably not your washing machine. Washing machine, your dryer does. Your dryer runs off. Your HVAC system works. Your electric water heater works off 240. Because those are your high wattage devices. They are designed to run around 240 volts. But I can use smaller conductors. So a lot of people say, what's the advantage of high voltage? And they say, more efficient. You pay for what? Power. So your loads are designed around a certain voltage. Everybody understand that? So if I took a 120 volt bulb and put it on a 240, it'd glow like that. If I took a 240 volt device and hooked it up to 100, it wouldn't do any work. It'd do a quarter of the work. So loads are designed around a certain voltage. The higher the voltage, the less current, which means I can run smaller gauge wires. So instead of running this big old wire, instead of running a 4-aught wire to run your water heater, I can do what? I can run like 8-gauge wire now. Because now I can run a smaller gauge wire. So high voltage means we can transmit our power with less what? Current. So what does Alabama Power do when they transmit that power? They run it through a transformer and step it up, which causes the current to go down to deliver that power, right? You understand? We're not talking about the load. We're talking about delivering power. If current goes down, that means instead of using copper, I can use what now? The fourth best conductor of electricity. Aluminum. Aluminum has quite a bit of resistance compared to copper. But if I use, what advantage does aluminum have over copper? A lot cheaper. Two different ways. Not only is it's readily available, easy to make, right? It's a lot cheaper and it's a lot lighter, which means now my big old towers out there don't have to support all that weight. So my towers are small to support all that, right? You understand? But now I can use aluminum to get it to you. And then the closer I get it to you, I'm going to have to go over to what's in the copper or my conductor to get to you. How do we get off on that? Transformers. So we have transformers. So over here we have 208. We have what we call a grounded Y connection, and you'll learn about that, the way you connect those Y connections. 208, but all our devices are 120, so what are y'all going to have to hook up on? You can't run 120 load on 220. So what are you going to have? Starts with a T. Transformers. Transformers that's designed to run a control circuit are called control transformers. So you can see all these right up here on the left-hand side, and you'll see those up there. Those are control transformers. But what it's going to do, it's going to let us step that voltage down to run our load. What advantage does low voltage have over high voltage? What advantage does high voltage have over low voltage? No, because I don't pay for two.
They favor it.
Yeah, so, but what's the advantage of high voltage? Less current to control the load, which means our watt can be smaller. Conductors, right? Don't need a break? Okay. I don't know if they sell some leather gloves down in the bookstore. They use them in air conditioning and refrigeration, I think. But just cheap little leather palm gloves, they're not very, very expensive. And you don't have to use them. The only thing you have to do them is when you're working on an active circuit. You don't have to do it when you're working on, while you're wiring the circuits up, just when you're making voltage measurements and stuff like that. When you're actually working on the circuit, that's the only time you'll need to wear your PPE. This is another one, voltage. So by the way, in formulas, we represent voltage with either V or E. Both of those are correct. Some books teach it as an electromotive force. So it'd be E is equal to I times R instead of V is equal to I times R. Those are current, amperes, 6.25 times 78 each electrons through the pass a point in the circuit at any one time. I don't know who measured that. Resistance, we have two types of opposition. We have resistance and reactance. Reactance we're just going to touch on so we can understand some stuff. In cable splicing, we'll have to deal with it a little more because we're dealing with conductors, and you can screw up with AC circuits just by running your conductors wrong, just by running them wrong. And so we got to really take into consideration that. Here we're going to deal more with this when we get into single phase motors. What's nice about these guys is they create a phase shift. To make a motor spin, you got to make, so electrical motors work on magnets. And we know that we know that like magnetic poles repel and opposite magnetic poles attract. Well, if I can take those and have one magnet in the center and then make this one move, then what's the motor going to do? It's going to turn. If one of them don't move, then the motor will just sit there and won't move. So you got to have a motion. One of the magnets has got to be in motion. DC motors, we let the motor switch itself. AC motors, the AC has to create what we call a phase shift. Well, that's what we can do with inductors and capacitors. We can create phase shift, which means now we can have single phase motors. Three-phase motors, three-phase, and we'll look at this, it automatically steams. So three-phase motors don't require any type of phase shift circuit. But single-phase motors, if we didn't have devices that created the shift in a phase, then there would be no such thing as a single-phase motor. And there'd probably be no such thing as single phase because motors are even a big part of your house, right? How many motors do you have in your house? Just think about it. Well, if you got an HVA system, you got at least two in there, right? You got air conditioning, you got the compressor motor, and you got the blower motor. So that's at least two motors. If you got a washing machine, it's got a motor in it. If you got a dryer, it's got a motor in it. If you got a dishwasher, it's got a motor in it. If you got a garbage disposer, it's got a motor in it. If you have any ceiling fans or attic fans, they got motors in them. If you have power vents, they have motors in them, and they're all single phase motors, right? So you got to understand a little bit about. And the name of this class is what? Motor control. So one of the main things we do, of course, is control motors. Now, there's more to that. We can control a lot of loads. So these guys that give us reactance, they cause phase shift. So we have what we call a capacitive start motor. We have what they call split phase motors. So split phase motors use XML or capacitor. Capacitor motors use capacitors. Those are pretty obvious. Why they didn't call the motors inductive motors? Why they call them split phase? I have no idea. And of course, y'all have all seen Ohm's law. Okay. Now, true Ohm's law is current times opposition, or opposition is equal to voltage divided by current. And current is equal to voltage over opposition. It's just what we're going to find out is we have two types of opposition in an AC circuit. We have what we call reactance, and we have what we call resistance. If y'all have had an ET100, then you're familiar with resistance. It's just that when you get into AC, you'll get very familiar with reactance if you take AC. AC is not required by the AUT. So we have to teach you a little bit about this to even be able to understand a little bit about AC and what's going on. So we won't be using much of these in this course. And we're not going to work these problems now. Voltage drop. An ideal circuit, all the fluids provided by the voltage source will be distributed across the load. Current flowing through the opposition of the load produces work or power that the circuit was designed to deliver. So your conductors are not delivering work, right? You understand? They have a function in life. The function in life is to get that current from the voltage source to the load. So what's the function of a conductor? Well, I just told you, right? That's its function in life. It's just like your blood vessels. What are those? What's your arteries in there for? To get the blood from your heart to your muscles. That's the only function they have in life. And of course, your veins are to get the blood from your lobes, right? Your muscles back to your heart. Now the problem is that there's no such thing that we understand. Real circuit, all devices have some resistance, or they might have reactance. Even conductors have resistance and reactance. So in cable splicing, we'll learn about the reactance and the conductor. Here, we're not going to deal a lot with reactance. We need to just understand a little bit what's going on. The amount of resistance a conductor exhibits to the flow of current is determined by what? The temperature. If metals get hot, their resistance goes up. If metal goes down, their resistance goes down. We've got a sensor called an RTD. It's a resistive temperature device. And we actually measure this change of current, this change of resistance with temperature to measure temperature. The physical size and the length. The material. You know we use two primary materials. We use what? What's the two primary materials used for conductors? Aluminum and copper. We're going to be using copper. Even though it don't look like copper, copper's got a big problem in that it oxidizes or rusts. A lot of people don't know the Statue of Liberty is made out of copper. Well, what color is the Statue of Liberty? Green. In fact, when they rebuilt it, they deliberately turned it back green. They exposed it to moisture so it would turn green because nobody would recognize a copper statue, a brass-looking Statue of Liberty. So copper oxide is an insulator. So that's one thing we have a problem with exposing copper to the atmosphere is it's going to oxidize and it gets rust on it and you have a problem, right? So a lot of your conductors are going to be tin plated, which means they don't look like copper, they look like silver. But if you took a piece of sandpaper and sand them, you get them off the wall, you see copper off. Of course, tin has a very low oxidation rate. Used to in computers, we used to code everything with gold. Everything that was exposed to the atmosphere was coded with gold. But then they finally realized that by the time we replace our computers, how often? I mean, how often do you replace your cell phone? So why use gold? Right? So why use gold? So they use a lot of tin plating now. So most of the stuff you take apart, they're going to be tin plated. Because they know by the time tin oxidizes, you're going to do what? You're ready to throw it away. So, the material it's made of, the size, and the length, and the temperature. So this is why Alabama Power don't insulate a lot of their conductors. Because if they insulated it, then the ampacity of would go down, right? Are you okay? So, reactance is determined by frequency. When current flows through, in and out of opposition, the amount of force available through the load decreases. This is called voltage drop. So this is the amount of voltage drop is equal to I times the amount of opposition in the circuit. So this would be an ideal circuit, and this would be a real circuit. So all your conductors have a resistance. There is conductors out there. They're called superconductors. Have y'all heard of that? Who has superconductors? The government, military has some. Some of their the Navy calls them railguns, but they're nothing but solenoids. But they don't hold a piece of metal in it. So what they do is they accelerate that magnetic field down that thing. What happens to that chunk of metal? Follow that magnetic field. And what do they do when they get to the end? They just turn it off. Shoot that chunk of metal out. So the Navy's been using that. They call them railguns. So if you ever have one, it's nothing but a form of cylinder. Superconductors are made of graphite material, and they have to be frozen to almost absolute zero to get your resistance down. So there's nobody here that deals with liquid nitrogen and that kind of stuff. So we don't run into superconductors. We're going to either use aluminum or copper, and aluminum and copper has resistance. What determines the resistance? The temperature, the gauge, or the size, and the length, right? And the temperature, right? I understand that. Everybody okay? So we have with this is called the American wire gauge. Some information they give you in American. So gauge numbers are strange. So what we do is we call it a bigger size wire. They call it a bigger gauge wire. Anytime you hear that, they're talking about a bigger size. But the problem we have is that they assign these numbers. Yeah, and it's a weird formula. I can show it to you. Use the exponents and all this other stuff. But basically, the gauge numbers, the bigger the number, the smaller the size. So a 20 gauge wire would be smaller than an 18 gauge. An 18 gauge wire would be bigger. The American wire gauge goes all the way from 50 gauge, which just don't go, all the way up to what we call it 4-aught. A 4-aught has a diameter of about a half an inch. And then what they do is they rate the resistance of the wire per 1,000 feet or per 1,000 per kilometer, wherever you're at. So you can see all these wires have resistance. And what I'm trying to do is if I'm an electrician, I'm trying to use the smallest gauge wire I can. Why is that? Cheaper. So yeah, I can run 10 gauge all over the place. I wouldn't be able to get it onto a 15-amp plug. Well, I guess you could. It'd be hard to run because it's pretty big. But I wouldn't be in business very long. So my ultimate goal is to use the right gauge wire, right? And the right size wire. So what we do is, so this goes up to what we call 4-aught, which has a resistance of about what? 49 milliohms per 1,000 feet. Or I could go down to a 20 gauge wire, which is 10.15 ohms per 1,000 feet. So if I was going to run it 2 inches, right? Don't understand. 2 inches, then a 20 gauge wire would handle a lot of current. Right? You understand that, and it still not get hot. If I was going to run that 100 feet, I can't, then if I try to put 20 up to it, it's going to burn up. It'll literally melt. Right? You understand that? Because it's ohms per 1,000 feet. And this ohms, by the way, they don't give you this. I need to get rid of this. This is the best chart right here. It's called the ampacity in free air, which means these are uninsulated. And free air is 20 degrees centigrade, which is about 60 degrees. So if I'm going to give you the resistance of a wire, I'm going to have to give it to you at a temperature. Because if the temperature goes up, resistance is going to go up. If the resistance goes down, temperature goes down, resistance goes down. So a good chart says, okay, this is the resistance at what? At 20 degrees centigrade. And then they give you an ampacity for that. And ampacity is its current carrying capability. Right? Understand. So how much current can a 20 gauge wire handle? It's got an ampacity rating of, I'm not saying, 11 amps in what? Free air, which means it's uninsulated, at what? 20 degrees centigrade. That makes sense. So what happens, what do you wear in the winter? Some of y'all are doing that. We insulate ourselves. What happens when we insulate ourselves? Do we get warmer or do we get colder? Okay, so if I insulate a conductor, is it going to get warmer or is it going to get colder? So this means the ampacity goes down with the insulator. Right? You understand? So what determines your ampacity is a lot of stuff. It's not only it's what temperature you're going to run the wire in and what type of insulation you use. So usually insulation is rated at higher voltage to hold that voltage in is probably going to lower the ampacity of the wire. And of course, this is a lot of reason why Alabama Power don't insulate this transmission. Where do they insulate them at? We're the only place to insulate that transmission. When it's on what we call a down drop, where it drops from your transformer, runs to your wall, to your house. Because you can touch it. And then plus they use the common or the ground as the guide wire. So the two lines are wrapped around the ground. So what they've done is we have something called NEC. Everybody ever heard of NEC? What's NEC? National Electrical Code. What do they do? What's the function of the National? No. No. What NEC does, NEC has two standards. The 70 standard is what NEC 70 standard is what most people understand. They call this the code. If you ever heard of that? That covers the safe installation of electrical appliances. It has nothing to do with your safety. It's the safe installation. What keeps you from burning down your house. OSHA covers your safety. Right? It has no care about what ampacity of the wire is or anything. It covers your safety. What they realized was that the National Fire Protection Association realized that they had no standards for your safety. So they came out with a NAFTA 70E standard. Now 70E is your safety, but the National Electrical Code, what we call NEC, that's the 70 standard. That has nothing to do with safety. Is it law? No. It is a recommendation. Before NEC becomes law, the authority having jurisdiction in your area has to adopt the code. If they don't adopt the code, it's not law. Okay, you understand that? Of course, OSHA has adopted, OSHA hadn't even adopted the 70E standard. But everything in 70E is in OSHA. Does that make sense? So a lot of your employers now teach 70E, which is arc blast. It covers electrocution. It covers arc blast and arc flash, which Mr. Sanders hopefully will show that. So what NEC has done is they came up with this table right here. This is safety standard, which sets the ampacity of the wire. All this up here is different type of insulation that you could get a 14 gauge wire in. Now, if we look at the ampacity for a 14 gauge wire, what does it say the ampacity for a 14 gauge wire is? 32 amps. NEC rates a 14 gauge wire at 15 amps. Huh? Well, no, these are different insulations. This is what the insulations are rated at. So this guy, this Romex, is rated at 60 degrees centigrade. So that means it's going to work okay until you get above 60 degrees centigrade. So that's not the rating of the wire. But you're right. What they've done, so you're right. But when you read to 60 degrees, that's not the rating of the wire. It's the rating of the what? The insulation. Now what they've done is that they've rated this for every possible, we call it die rating. It's dropped down by a certain percentage depending on what's going on. So what they've done is they've die rated the 14 gauge wire just about any situation you would run into installing this thing in a house. Under 100 feet. So as long as the run is under 100 feet, as long as you install it in a house, you can run it through the ceiling, you can run it under the bottom, you can run it through the walls. It's rated at 15. So they die rated it so you can run in any situation. If you run it over 100 feet, then you're going to have to get out tables and you'll probably have to go to a 12 gauge wire. See, so if you do house wiring, then we call 14 gauge wire, 15 amp wire. So a 15 amp service is going to run 14 gauge wire. A 20 amp service is going to run 12 gauge wire. Even though 12 gauge is probably rated at pretty close to 50 amps in free air, right? You understand? At 20 degrees centigrade. But what's the odds of me being 20 degrees centigrade and say that out loud? Slim to none, right? We're getting there now. We stay in the 70s. I think last week we were up in the 80s. So that's Alabama. So, but anywhere in the United States, even up in Canada, their rate is wire the same. So that means this is good for just about any situation you could possibly go in a residential situation, right?
So this is available online, by the way. It's the 1013A.
Oh, guys, we're fixing it. Now, I think what we're going to do, this is work, and we're fixing to get into a whole nother section about shorts and opens, and Mr. Sanders can do that. Shorty.